This is section 11.7. We are studying the gas laws, and we're looking at the relationship between the different components, mostly volume, temperature, pressure, numbers of moles of gas, how much gas is actually there. And this is named after Avogadro. Avogadro is the one that we studied earlier, where we had Avogadro's number. 6.022 times 10 to the 23rd numbers of molecules in a mole. Okay, so we'll see that numbers of moles is just how much you have, how much gas do you have, how many units of gas. We could do it that way. So there couldn't be anything easier than this. All of this chapter is easy. Every section of it's easy. If I'm blowing up a balloon and I put more air in the balloon, what happens to the volume of the balloon? Yeah, these are directly related. More moles in means more air in, more gas in. If you have more gas in, the volume has to expand to make up for that gas. So if you're blowing a balloon, the volume has to increase. Okay, if all other things stay the same. So in order, for instance, a balloon is a great example, because if I blow up a balloon, the increase in pressure, the increase in space of volume allows my pressure to be the same as it was. Okay, if I'm blowing into something that's a definite shape, and I blow more air into it, then what happens is the pressure has to grow up. Like your tire. Your tire doesn't want to blow up. You want the tire to be the same shape both times, and by not allowing the shape to change, it increases the pressure in the tire, and that's what we would actually after. But in this case, we're looking at moles of gas and volume. As you increase the moles, volume goes up. That means it's directly related. So volume is on the left of the formula, and moles, which is the little letter N here, will be on the right. Okay. Now, if you only extract that to V and N, since V was on the left and N was on the right, you bring N down and make it into a fraction. So just like we did T's, all the T's are always on the bottom. Well, N's will be on the bottom. Okay, so V's, V1, N1, V2, N2. And that's your formula. Now, whatever you solve for, get it by itself, everything else on the other side, then fill in the other three. You'll be given three pieces of information, solve for the other. So if I have 0.75 moles of helium occupies 1.5 liters, so that's how big the balloon is, what volume when you make it 1.2? Well, if I increase it from 0.75 up to 1.2, I've increased the volume. That means I'm going to increase, or if I increase the moles of gas, I'm going to increase the volume. So it's a direct relationship. Okay, so to do this, I have to realize that I have a formula. V1 over N1 equals V2 over N2. I find my numbers, okay? And then once I solve for V2, I simply put in the other three, and that's how you get your answer. You just plug and chug. Okay. STP means standard temperature and pressure. Standard pressure is 1 atmosphere. So imagine me boiling water on my lab table, okay, at sea level, where the air is above me. That's standard. Standard just means something that everybody can put their brain around. A boiling pot at sea level is going to boil at a certain temperature, and that temperature is going to exert a certain pressure, etc. Right? If I change that sea level, then I've monkeyed with everything. All the temperatures change, the pressures change, everything changes. Standard temperature is 0 Celsius. So in the situation where you have 1 atmosphere and 0 Celsius, that's called standard temperature and pressure. And standard meaning as long as these parameters are exactly the same, everybody in the world could figure this out. Okay? Because standard pressure means 1 atmosphere. or 760 torr or whatever. Standard temperature is 0 Celsius, which is 273 Kelvin. So that's just, when you say STP, my mind instantly says, okay, 0 Celsius, 1 atmosphere. And then I convert to whatever I need based on that. If you have standard temperature and pressure, something is very cool. No matter what gas you're talking about, you're going to get the same volume. So at 0 Celsius and at 0 Celsius in 1 atmosphere, you can guess the volume. In fact, it will always be the same. It's 22.4 liters. When you put 1 mole of gas in a balloon, for instance, at 0 Celsius and 1 atmosphere pressure, you're going to end up with a balloon 22.4 liters big. That's what's going to happen. Now, really, this is just a problem like any problem. Okay, instead of going up to 18 degrees or 5 degrees or 30 degrees or whatever these other problems we've done, we simply went down to 1 atmosphere and 0 Celsius. And in such, the answer to the problem of how big it was is 22.4. Well, as long as we know it's standard, it's always going to be 0 Celsius and always going to be 1 atmosphere. Under standard conditions, 1 mole is equal to 22.4 liters. So you can guess how big the box is at standard. Okay, that's kind of where this is going. Now, since it is an equation, or since it's an equality, you can make a conversion out of it. So if 1 mole of gas is 22.4 at standard temperature and pressure, what's 2 moles of gas? Can you see that you can almost do this in your head? If you double 1 going to 2, you're going to double 22.4 to 44.8. So it's a relationship that you can make a guess for. Okay. So, what's the volume occupied by 2.75 moles of gas at STP? First of all, it doesn't matter what kind of gas. All gases are the same. They act the same. And at STP, I know that the volume of gas is 22.4. So I can simply do it like a fraction. I can use it just like a conversion factor. I say 2.75 moles, 1 mole to 22.4 gives me the new liters. This way I don't have to do all of the gas laws. I can go straight to volume as long as it's at STP. If it's at STP, it's easy. How many grams of helium gas are present if 8 liters of helium at STP? Well, that means I have to know how many grams are in a mole. And to do that, you have to go through the periodic table, right? You need to know how many liters there are, and then how many moles there is, and then how many grams per mole. What you're going to see is that all that information is staring you in the face on the periodic table. All right? There's a number under every atom, that atomic mass, and that will be the grams of 1 mole of that material. So when you look at the periodic table and there's a number straight under the symbol, that atomic mass, that's the amount of grams of that material in 1 mole of that material. All right, so you can go straight to moles as a result, and we'll do these later on. And so you would first of all know that in 1 mole there's 22.4. Okay, and then once you break it down, you're going to say in 1 mole there are 4.3 grams of helium. That's from the periodic table. You would actually look on the periodic table and see if we're only talking 1 mole, then the number underneath helium is 4.03. When you break everything, when you do all the multiplication on the top, division on the bottom, you end up with an answer of 1.43 grams. And we'll do these types of things later. Also, you can do density. Okay, remember density is mass over volume. So what's the molar mass? The molar mass is going to be that mass of 1 mole. It's the number under the symbol on the periodic table, and it's molar volume. If you know it's 22.4, you know its molar mass on the periodic table, and you know it's 22.4 of 1 mole of gas, you could do the density of that gas. And you could know, is this gas going to inflate a balloon and rise in the air or sink in the air? You could compare one gas to another gas. That's pretty amazing. Okay, so calculate the density of oxygen at STP. Well, 1 mole of oxygen is 22.4 liters. Okay, so I already know its volume, so 22.4 on the bottom, and then grams per liter, how many grams of oxygen. I'd have to go to the periodic table, know that each one of these oxygens was 16, and there's 2 here. So the periodic table says 16 under carbon or under oxygen. So 16 to 16 is 32. So I would have 32 on the top, 22.4 on the bottom, and then that's how you find density. You end up with 1.43 grams per liter. All right, so this is always a preview, and then what we'll do in class is doing our push-ups. All right, thanks.